Good afternoon, my name is Artem Nureyev. I am a researcher at Kazan Federal University. Today I want to present you the results of our research that was focused on the analysis of elastic flexural vibrations of beams in the fluid. The motivation or the research comes from different practical areas such as atomic force microscopy, energy harvesting, design of MEMS devices, cooling systems, and biomimetic propulsion. The global goal of the present research is to understand the mechanism or the interaction of the beam with the fluid. In this presentation, we will discuss the several main factors which have a strong influence on the structure of the flows induced by the oscillations of the beams and on the corresponding hydrodynamics forces. After the problem statement and the presentation of three-dimensional numerical model, we will talk about the influence of the length of the beam, about the quasi-two-dimensional flow model, about the influence of amplitude and frequency of oscillations, and finally we discuss the ground effect. Let's consider the flow around a thin cantilever beam with length L and width B performing flexural vibrations in a viscous and compressible fluid in the first natural mode near a plane boundary. Normalizing the spatial coordinates time and velocity, we can write the governing system of the equation of the fluid in the form of the Navier-Stokes equation, equation number 1. Here beta and Kc is the dimensional frequency and the amplitude of oscillations. L is the dimensionless length for the beam. Sigma is the ratio or the gap distance between the plane boundary and the beam and width of the beam. To describe the motion of the beam in the fluid, we use the classical Ehlers-Bernoulli theory. We also assume that the hydrodynamic forces are small in comparison with the elastic ones, and that the resonant oscillations occur only in the first natural mode. In this case, the movement of each point of the beam at an arbitrary moment of time in dimensionless variables can be described by formulas 2 and 3. We solve the problem numerically. The realization of the computational scheme was done on the basis of OpenFOAM package. Simulation of the beam oscillations was carried out in a limited region, which is bounded by a rectangular parallelepiped. The external boundaries of the region was considered as impenetrable. On the surface of the beam and on the plane boundary, no slip conditions was specified. For the discretization of the computational domain, the dynamic meshes were used. This video shows the movement of the mesh in YOZ plane. The calculation of the velocities of the mesh nodes in the domain was carried out on the basis of the solution of the Laplace equation with a variable diffusion coefficient. For the discretization of the fluid motion, we use second-order numerical scheme. Our research shows that the relative length is one of the main parameters affecting the flow. To identify the characteristic features of the hydrodynamics near the beam, let's consider the period average flow patterns that describe the secondary streaming. The secondary streaming is a general mechanism of the mass transfer in the region. We visualize the secondary streaming using massless particle traces. This slide shows a steady streaming around a short plate. The main structural feature of the flow, let's look at the video, is 4 vortex tubes that are formed above and below the lateral edges of the beam parallel to the main axis. The average velocities of such flows in longitudinal and transverse directions are of the same order, so the flow is essentially three-dimensional. For long beams, most of particles released near the beam after passing a short distance along the beam leave its boundary region and enter the outer flow. Such behavior clearly indicates the dominant role of transverse flows. The zones where transverse flows are absolutely dominant we will call quasi-two-dimensional zones. They cover up to 3/4 of the beam. All regions are localized in the quasi-two-dimensional zone around the beam are similar to the key two-dimensional flow regions formed around oscillating rigid plates. For example, let's look at the flow structure. For the case beta equals to 200 and Kc equals to 6, which seems to be quite complicated at first glance. In fact, it is formed mainly by two quasi-two-dimensional regimes. The first of them is the symmetric regimes that can be localized in the zone of small local amplitudes of oscillations closer to their fixed end. The second is the so-called cyclic diagonal flow regime that can be localized in the zone of large local amplitudes of oscillation closer to the free end of the beam. To systematize the data on the flows near the long beams, as well to analyze the changes occurring in the quasi-two-dimensional zone with variation of the frequency and amplitude, a map of the flow regions was constructed. Here in this map, the different types of markers indicate the different types of flow structure. All flow regions in the quasi-two-dimensional zone are practically the same as the key two-dimensional flow regions formed around oscillating rigid plates. In the next step, let's consider the hydrodynamic forces acting on the beam. For the analysis of the inline force, we use the Morrison expansion, which can be written in the form of the equation 4. Here, the first term in the equation 4, which is proportional to acceleration, describes the added mass force that affects on the resonant frequency of the beam. The second term, which is proportional to the square or the velocity, describes the drag force that is responsible for the hydrodynamic damping of the vibrations. In the present slide, we show the variation of the local values of the drag coefficient along the beam depending on the value of the oscillation amplitude of the cross section. As one can see, the longer the beam is, the closer the local force coefficient becomes to the two-dimensional estimates. The same can be said about the coefficient of added masses. For long beams, the local values of the coefficient of added masses is practically the same as for the plane flows. As the beam approaches the plane boundary, vortex structures begin to interact with the boundary. For short beams at moderate vibration amplitudes, this creates the streaming along the boundary. For long beams, interaction with the plane leads to partial degradation of the quasi-two-dimensional zone. For example, the represented flow near a beam of length 10 can no longer be considered as quasi-two-dimensional, as it was in unbounded fluid. These visible changes certainly affect the hydrodynamic forces. The values of the drag coefficient begin to change significantly as the gap to width ratio decreases to 1. The results of this the results of three-dimensional modeling indicate a significant increase of the values of the drag coefficient, especially in the region of small values of the local amplitude of oscillation. The enhancement of the role of the three-dimensional effects in the venicity of the plane boundary significantly reduces the accuracy of the quasi-two-dimensional model for estimating of the drag coefficient. In contrast to the drag force, the added mass force in the considered range of parameters slightly change with the decreasing gap distance to the plane boundary. The dependence for added mass coefficient obtained in the framework of two-dimensional and three-dimensional models are in good agreement. In conclusion, I would like to thank you for your attention and to present several of our recent publications on this topic. Thank you again.